All right, so the last topic in the equilibrium chapter is this thing called the Chatelier's principle. And this is a big deal. So me personally, I have a theory. If there is something that is some sort of universal truth, it's something that you probably picked up from one of two people, either your mother or your kindergarten teacher. And this is one of the mom things usually. Now, if you look up Le Chatelier's principle in the book, you'll see, or any chemistry textbook, you'll see something like this phrase right here. When equilibria are disturbed, the system reacts in a way to counteract the disturbance and return to equilibrium. Now, this is 100% true. It is also 100% boring. And I prefer the translation that the way my mother said it, which would be what she said when my brother and or I would disturb the delicate equilibrium that was her household. And it was Gérer, mais comme c'était avant, Jacin, toi aussi. Remember, my family is Quebecois, so we got yelled at in French. In English, that translates roughly to put it back the way it was. Give my mother the attribution for that quote. And another thing to point out is that we're talking about a return to equilibrium, but it's not. Returning to equilibrium is not the same thing as completely negating the change that you did to disturb the equilibrium. So going back to mom's example, yeah, we could try to glue the vase back together again, but it was by no means exactly the same as it was before when we broke it. So let's take your and your siblings' hijinks and translate them to chemistry. Now keep in mind, this is actually the reaction quotient, but without numbers. So consider some generic, very generic equilibrium system, reactants and products going back and forth. And so the rule is simply that whatever the disturbance is, the system will try to counteract it best it can. Now, chemical systems, such as this one, have only two options. They can react in the forward direction, converting reactants to products, or they can react in the reverse direction, converting products to reactants. That is it. So for example, if the disturbance, sometimes you have a system that's already at equilibrium and you add more reactant. Well, how do you counteract that disturbance? Well, you want to get rid of it. How do you get rid of it? Well, between reacting forwards or backwards, forwards is the way that gets rid of reactants, but also at the same time will make some products. And so that we say form products. Now there's a few ways that we also say pretty much the same thing. We can say that we react forward, that we shift to products, or we also say shift right sometimes. Now maybe you added a product. Now the way that you would minimize that disturbance is you would whisk the product away, and that is done by reacting in the reverse direction. But again, so that's going to react away the extra product, but also make more reactant than you had before as well. So that's what I mean about not going back necessarily to the exact same equilibrium composition. And so one of the other chemically relevant, so I'm going to talk about two more chemically relevant stress test equilibrium here. You could also increase the pressure. And so the idea is that you're going to react in a way that will reduce the pressure. And that actually depends on the reaction stoichiometry. And now remember that the pressure that a chemical system is going to be under is a function of the total amount of gas in the system. So the rule here is that if you increase the pressure, you're going to shift to whatever side happens to have the fewest number of gas moles. And the other thing, this is the last little topic here, is that heat. So sometimes you can ask, if I increase the temperature, is that going to shift one side or the other? Now you've learned about thermochemistry a little bit, and now you can answer that. Think of heat as a product or reactant. Heat is a reactant for endothermic processes, those that take in heat, and it's a product for exothermic. So these are, and that hopefully that's not too hard to see. Exothermic reactions give off heat. So think of heat as a product there, and then these rules apply. So I'm just going to give you an example real quick of all of these and some other variants on it. So we've had a lot of nitrogen-oxygen containing reactions today. There's about 7 different NO compounds. I think actually you might have seen almost all of them, except N2O5. But so we have NO2 reacting with nitrogen dioxide. I'm sorry, N2O, dinitrogen monoxide, reacting with nitrogen dioxide to form 3 moles of NO, with delta H or Q being a positive 155.7 kilojoules. And so get a sheet of paper ready. So consider if we had an equilibrated mixture of these 3 gases. And by the way, let's see. These are all really toxic. If you inhale these, you will turn the fluid in your lungs weakly acidic. Your body's reaction to that is to dilute the acid, which puts more fluid in the lungs, so you kind of drown internally. This stuff, if you breathe it, you start to giggle and get a little silly because this is laughing gas. All right, so for each of these, I'm going to give you 3 options. If I do this to an equilibrated mixture of these 3, which of these will happen? So think about it, make your choices, and come back when you're done. Welcome back. So if I add N2O, you want to get rid of it, and the way that you get rid of it is by reacting forward. So that would be a shift to the right. Now, along with adding components, you could also take them away. So what would happen if I removed NO2? Well, the way that you try to offset that change is you want to put some back. And the way that you would do that is by reacting in the reverse direction, which would say which shifts to the left. If I added NO, the way to offset that would be to, again, get rid of it, which is also the reverse direction. So we'd say shift left. Now, what about increasing the temperature? Well, there's your hint right there. Delta H, or Q for this reaction, is positive. This is endothermic. It takes in heat. So you want to treat heat as a reactant. If you are increasing the temperature, you are adding heat. You're adding more reactant. The way that you get rid of that is you react in the forward direction. So that's going to shift to the right. Now this is one of the more complicated ones. What about decreasing the volume? So these are all gases. Volume and pressure are related. So if we are decreasing the volume, that is akin to increasing the pressure. And which side is it going to go to? So here's where we figure out which side has more moles of gas. On the product side, we have 3 moles of gas. And on the reactant side, we only have 2. So the way to minimize or mitigate the pressure increase is you shift towards that side, to the reactant side. So it would be a shift left. And the last one, the sneakiest of them all. What if I added helium at constant volume? So let me give you a hint. Write down the equilibrium constant expression for this system. And go ahead, I'll wait. All right. If you had the concentration of NO cubed divided by the concentration of N2O to the first power divided by the concentration of NO2 to the first power, congratulations, you're right. Now, does helium show up anywhere in that expression? No, it does not. So components that actually aren't part of the equilibrium system have no effect on that equilibrium system. So even though this would increase the total pressure in the container, it doesn't increase the partial pressure of any of these, which is what the concentration of those depend on. So it doesn't matter. And so things that aren't directly involved in the chemical reaction have no bearing on it and therefore no change. All right, so this is the beginning and the end of the equilibrium stuff. The next, which will actually be after this, now we only have one more, I think, major content area to get, and that's going to be acids and bases from an equilibrium standpoint. So I will see you then, and again, remember Casey. All right, see you next time.